Asked to find the remaining zeros of this polynomial given this is a 0. We will start this off with synthetic division to get this down to a quadratic. So the negative 4 is a 0, that'll go on the outside. 1 for the x cubed, 9 for the x squared, 17 for the x, negative 12. Drop the 1 down, multiply and add, continue in this way. And then we get down to a quadratic that is x squared plus 5x minus 3. Now it looks to me like this is probably not going to be factorable. If I try to think about things that multiply to make negative 3, I don't really see how I'm going to get this 5 in the middle. So I am going to have to bust out that quadratic formula, which means I will have to start off with b squared minus 4ac, which in this case will be 25 minus 4 times a times c. If I pop that in a calculator, 37 will be looking back at me if I did it correctly. And that's not a perfect square, so I was right, this wasn't factorable. And that means the remaining zeros will be x equals the opposite of b, plus or minus the square root of that value we just found, all divided by 2 times a. 37 is not, it's a prime number. More importantly, there's no perfect squares that go into 37 at all. So this radical is not going to simplify any further. And that disgusting monstrosity, that's our final answer. We're not going to make it a decimal, we're not going to simplify it. It's just that the quadratic we got in the end ended up not being factorable, and so we have this grossness to look at. Since this problem says find the remaining zeros, we don't need to include the negative 4 in our answer, but if you threw that over there as well, I wouldn't hold it against you.